Okay, this is a continuation of WA13 D for Chemistry 1 at West Lafayette High School. We're going to pick up here with problem number 5. We covered 1 through 4 earlier. Just to recap here briefly, we talked about these in class, but just to reintroduce, this assignment mainly is dealing here with molality, which is moles of solute over kilograms of solvent. The freezing point changes that occur as one of the colligative properties. So the delta TF is the change in the freezing point and the change in the boiling point, delta TB, and then osmotic pressure. So here are the equations. If you need to come back and look at it at about 50 seconds in the video, if you need to see the equation or see some of these constants or something like that. Okay, so onward to number 5 right here. We have a sucrose solution. Sucrose is C12H22O11. It's a molecular compound, so it has a Van 't Hoff factor of 1. We'll need that later on for the freezing point, boiling point. We have 135 grams. We have 1.70 liters of solution. This is different than the previous problem number 4 in the other video because this says the total volume is 1.7 liters. So this is not the volume of just the solvent, which is what we were given in the previous problem. So this is going to be a little bit trickier, take a little bit more effort to figure out just the kilograms of solvent. So that'll be a little bit different. Once we get that, then we'll be able to find the molality, and with the molality we can plug into the delta T and delta TF. There's not a lot of room here in this space, so I'm going to pull up another sheet of paper here to kind of work from. We'll keep that problem right up there, and then we'll kind of go from there. So we're going to start by converting the 135 grams right here to moles. So 135 grams of NaOH. No, I'm sorry, of C12H22O11. And we're going to convert that using the molar mass of C12H22O11. And so that is 12 carbons at 12.01 and 22 hydrogens at 1.01 and 11 oxygens at 16.00. That adds up to 342.34 grams. So that gets the moles. Let's take that 135 grams and divide by that previous answer. That gives us 0.394 moles, keeping 3 sig figs of C12H22O11. All right, so that's the moles. We'll consider that kind of the first step right there. The second step is going to be to figure out the number of kilograms of solvent. And we're going to start with that 1.7 liters of solution. I'm real big on showing your work and showing the units and labeling things properly. So I'm labeling this solution so that we can keep track when we've got solution, when we've got solvent, when we've got solute. In this case, we've got solution. They've given us also up here that we have a density of 1.06 grams per milliliter. We're going to use that as a conversion factor in just a bit, but notice it's grams per milliliter and I have liters here. So let's first get that liters to milliliters. There's 1,000 milliliters to a liter. And I'll just keep this solution in there as a way of, again, properly identifying what I'm working with at the time. Now I can use the density, 1.06 grams of solution for every 1 milliliter of solution. So the milliliters of solution cancel out. And what I actually am after is kilograms of solvent. Right now I'm at grams of solution. So let's get that to kilograms of solution. It's not the only way it can be done, but there's a good mathematical reason for doing this, which shows up here in just a second. Let me finish writing this out. Kilograms of solution. And so the grams of solution cancel out. That gives me kilograms of solution. Notice that mathematically now, the 1,000 over here in the bottom cancels with the 1,000 over here in the top. So in my calculation, all I'm really left with is the 1.70 times the 1.06, and the units are kilograms of solution. So That's the 1.70. Just get that over. Kind of a glare there. 1.07, 1.70 times 1.06. That's 1.802. I'm going to put that little 2 as a small little number there in case I decide to use it later on in my calculation, but those big numbers are my sig figs. Now that's only kilograms of solution, so I can't yet use it to find molality. I have to then subtract off the grams of solute. So this 1.80, if we got that down there, this is kilograms of solution. And I need to subtract off of that the, right up here is the grams of solute. Let me convert that to kilograms. It's just 0.135. If I move the decimal 3 places to the left, 0.135 kilograms of solute. If you subtract the solute away from the solution, that leaves you with the solvent. So that's the 1.802 minus the 0.135. Now the sig figs here, or here's what the calculator gives me. It's 1.667 kilograms, and this will be solute. Now, and this will be solution. So this will be solvent, which is what we're after. So that's 1.667. Now when you consider the sig figs here, they go out to the second decimal place, and here they go out to the third decimal place. So we can only keep to the second decimal place right there. So it should really round to 1.67 kilograms of solvent. So now that we have the moles up here of solute, and now we have the kilograms of solvent, we can find the molality. So that is 0.394 moles of C12H22O11, and that's divided by 1.67 kilograms of our water. That's our solvent. And so 0.394 divided by 1.67. Again, at 3 sig fig, 0.236 molal C12H22O11. So now that's not an answer, but that's a big step right there. So that's where we are right now so far. So that's step 2, and that's quite a bit of work there just to get to the molality. It was easier in the previous problem because we didn't have to do all of this stuff. We were right here. Okay, the next step then, because we're trying to get the freezing point and the boiling point, is those 2 parts right there. And so here, and I'll identify this here as part 3, I guess. We're going to find the freezing point delta TF is equal to I times the KF times the molality. And in this case, the Van Hoff factor is 1 because glucose or sucrose, C12H22, is a molecular compound. The KF, this is being dissolved in water, so it's 1.86 degrees Celsius per molal unit. And our molality, we just calculated 0.236. So notice the molal unit cancels out, and we can multiply that 1.86. Slide that up here. So we can multiply that 1.86 times 0.236. And that's 0.439 degrees Celsius, keeping 3 sig figs. Now that is our delta T. That is not our new freezing point. Since this is from water and it's always a freezing point depression, it's going to push the freezing point lower, then we need to subtract that from 0 degrees Celsius. So 0 degrees Celsius, 0.000, because the freezing point of water at 0 is defined so we can keep an unlimited number of zeros there to make the sig figs work in our favor, or keep as many as possible. So when you simply subtract that, it's negative 0.439. Not really something you need to write out, but I just trying to be thorough here. So that right there is your freezing point, and that's what you're able to put in to Weber sign. The boiling point is essentially done the same way. We'll count that as step number 4 over here. We're going to use delta TB and KB here. Van Hoff factor still 1, of course. Now 0.512. the boiling point effect is not as significant, so it's only 0.512 degrees Celsius per molal. And our molality is 2.236 molal. Molal units cancel out. And we have 0.512 times 0.236. That is 0.121 degrees Celsius. In this case, it is this is boiling point elevation, so boiling points get pushed up. So we're going to add this to the 100. And again, 100, we can take as many decimals as we need. So when we add that to it, we get 100.121. The rule for addition and subtraction in sig figs is not how many do I get to keep, but it's to what place I get to keep sig figs. So these are both, this is out to as many zeros, as many sig figs as you want to make them. We don't need all of these other zeros out here, but we need 3 to match the 3 that we already have in our delta T calculation. So we have 100.121 degrees Celsius, and that is our second answer for the boiling point. So anyway, so there's our calculation. Let's see if I can zoom out there and there we go. So there's the entire calculation. Bit of work for that one. So little assistance on that one is, I think, warranted. Okay, let's. So that was number 5. Number 6 and 7, similar to each other. Get back in here a little bit. An aqueous solution containing 44.2 grams of an unknown molecular compound in 177.9 grams of water was found to have a freezing point of negative 2.1. Calculate the molar mass. Now, typically we find the molar mass from the periodic table because we know the substance. This is kind of in reverse. And what we should, I guess, kind of think about is, how do we find molar mass? Let's see. I'm going to... Where's that other piece of paper? I'll just use this for now. So to find the molar mass, let's jot that down here. So molar mass, when we get it up off when we get that off the periodic table, it has units of grams per mole, and that essentially is kind of our little equation. We need the number of grams on top, and we need the number of moles on the bottom. They've given us the grams right here, so we have the 44.2 grams of our compound. On top, we need to find the moles of the compound. That's really the task here before we can finish it off with this. The fact that they've given us a freezing point of negative 2.1 in water is a pretty significant clue that we're going to use the delta T F equation. So let's kind of start there. This is not our starting point. This is how we're going to end. It's going to happen at the end of the problem right here. So we're going to start with calculating we're going to start by using the equation delta TF equals I times KF times the molality. And let's just identify what we know. We know that we have a freezing point of negative 0.21, which means that the delta T must have been 2.1, and then it was subtracted from 0 to get that negative 2.1. So this is 2.1 degrees Celsius. The Van 't Hoff factor is going to be equal to 1 because it's a molecular compound. That means the Van 't Hoff factor is equal to 1. It doesn't split up into ions. It's in water, so we know the KF is 1.86 degrees Celsius per molal. And the molality is what we're solving for. That's kind of like our X right there, if you will. And so let's solve for the molality. So the molality is just going to be the 2.1 divided by the 1.86. And we're at 1.13 to 3 sig figs. We can only keep 2 sig figs actually, so I'm going to write that, I'm going to keep this number in the calculator for a second because I'm going to use that next, but I'll write this as 1.13. And what I like to do sometimes is put a bar over the 2 digits that are sig figs because this isn't the end answer. So I like to round at the end. So we have the molality. Remember that molality is equal to the moles of solute over the kilograms of solvent. And we can use that. We can use that as a conversion factor to help us work this out. Notice we've got, again, 179 grams of water up here. So as kilograms, that is, move the decimal 3 places to the left, 0.1779 kilograms of H2O. So we're going to use that up here as a conversion factor. And 0.177, we're going to use the conversion factor to work with that number. That's kilograms of water. Let's clean this up here. 0.1779 kilograms of water. Now we're going to use our molality here. 1.13 moles of our unknown compound, so that's our compound, for every 1 kilogram, right? That's what molality is, moles per kilogram of solvent. Our solvent in this case is kilograms of water. So notice that the kilograms of water cancel out, and that leaves me with units of moles for my compound. So let's figure out those numbers. 0.1779 times 1.13, and that gives me 0.201 moles of my compound. So that right there is going to drop that in right up here now. That's going to be my end now. So 0.201 gives me my grams and my moles. So I can take the 44.2, divide that by the previous answer there, and that gives me 219. Rounded to 3 sig figs is going to be 220. I want that 0 to be significant, so I'm going to put a decimal after it. You could also use scientific notation, and that's grams per mole of the compound. So that's our final answer right there. All right. So we started here, used the freezing point and the equation to figure out the molality. We then used the molality as a way to get from the kilograms of water to the moles of the compound. And then once we had the moles of the compound, we combined it with the original grams that was given in the problem, 44.2, to get the molar mass. All right, cool. All right, number 7 is done pretty similar to that. Looking for something significantly different. You got a freezing point just like we did up here. 6 kilograms of water, similar to the grams of water up here. Some ethylene glycol is added. The big difference here, it looks like, is we got the freezing point. So in a similar manner, from the freezing point, we're going to be able to solve for the molality. And then when you have the molality, you can figure out the moles. Oh yeah, here's the big difference. When you figure out the moles of your compound, we know that it's ethylene glycol, so you can add up the molar mass of this compound, and then you can use the molar mass as that next step and convert from grams to moles. So from moles to grams. So you can put, for every 1 mole of ethylene glycol, you can add up its molar mass and put the grams of ethylene glycol right here, and that'll give you the grams that they're asking for. So it's kind of a similar. It's 2/3 of the problem is pretty much the same. This stuff is all pretty much the same, and then instead of figuring out the molar mass, you throw on one more conversion factor down here to convert from grams to moles. Number 8 and number 10, I believe. Let me see. Let me find the next page here. Yeah, number 8 and number 10. Let me fold this back. There's 8 and there's 10. Number 8 and number 10 are similar problems. They're asking you to arrange some solutions in order of decreasing freezing point here in number 8 and increasing boiling point here in number 10. I put a note in the instructions here that here you'll notice the lowercase m's, those are molalities. Here they're capital M's, those are molarities. But for the sake of keeping these two pretty much the same kind of problem, just assume all these molarities are molalities, and the thought process then becomes pretty similar. We talked about this one in class. It essentially has to do with the Van 't Hoff factor and taking into account the Van 't Hoff factor for each one of these. So what you could do is actually go ahead and calculate. They're all in water. So you could go ahead and calculate the actual freezing point for all 4 of these and then simply rank them. And that's okay. It takes a little bit of, a couple of minutes to do each one of those possibly. Maybe not. You get the hang of it. The Van 't Hoff factor is essential in this one, though. In fact, this is the first problem where the Van 't Hoff factor plays a role other than being 1. And so for ethylene glycol, the Van 't Hoff factor is 1 because it's a molecular compound. But for K2SO4, when it dissolves in water, it breaks up into 2 potassium ions and a sulfate ion, SO4 2-. And that's a combined 3 particles right there. And so that has a Van 't Hoff factor of 3. That's essentially what the Van 't Hoff factor is how many particles do you get in solution when a mole of this stuff dissolves. When MgCl2 dissolves, we get, kind of center this a little bit there. So you get an Mg ion, Mg2+, and you get 2 chloride ions, 2 Cl-. It's not a Cl2 ion, it's 2 Cl-. And so that also has a Van 't Hoff factor of 3 because there are 3 particles. And when potassium bromide dissolves, you get a potassium ion, and you get a bromide ion. And that is 2 particles, and so the Van 't Hoff factor is 2. Now, when you take into account the molality of the solution and the Van 't Hoff factor, when you combine those two, remember the equation is delta TF is equal to I times Kf times the molality. Well, I'm going to move this Van 't Hoff factor. I'm going to move that over here to the right there. We're going to take these two terms and kind of merge them together with the actual numbers that are given. All of these would be multiplied by the same Kf, 1.86. So really, since that's going to be comparable for all 4 of these, if we just simply figure out the molality Van 't Hoff factor combination, what's the magnitude of that combination, we can rank them without actually going all the way to the freezing point. So here is a point 2 with a Van 't Hoff factor of 1. So the net effect here for this first solution is 0.2. That's for the ethylene glycol, letter A. And for the letter B, it's 0.14 times a Van 't Hoff factor of 3. Well, that's 0.42, right? So 0.42 for letter B. Letter C, MgCl2, we have 0.1 as the molality with a Van 't Hoff factor of 3. That's 0.3. I'll put 0.30 on there to keep decimal places similar looking. And 0.14 for the KBr is the molality times the Van 't Hoff factor of 2, puts it at 0.28 for letter D. And so since they would all be multiplied by the same 1.86, the most significant impact is going to be the largest magnitude number that we've just computed here. So that's going to have the most significant impact. And then that, and then that, and that's going to be the smallest impact. So when you're arranging these in terms of decreasing freezing point, this will be the most negative, and therefore that's going to be the lowest one. It should be the last one that you write. When you look at number 10, it's going to be done in a similar way. It's only got 3 compounds here, but make sure you take into account the Van 't Hoff factor. Number 11 is number 11 and 12. Oh, wait, we're going to go back to number 9 here. That's right. Number 9 is a little different. Here at number 9, we have some similar calculations, freezing point and boiling point, to what you had up above. And now that we've talked about the Van 't Hoff factor, notice the Van 't Hoff factor here for sodium hydroxide is going to be 2. And the Van 't Hoff factor for potassium bromide right here is going to be 2. Everything else has Van 't Hoff factors of 1. They're all molecular compounds. The big difference here is that this is being dissolved in ethanol, not water. This is being dissolved in chloroform. That's the name of that compound, and not water. There is a table of molal, boiling point, elevation, and freezing point depression constants in your web assignment. That is a link directly to the table of information that you need. I do not have that printed out, so I really can't take this much further than that. But these are just freezing point, boiling point calculations with a substance other than water. So pay attention to the boiling points, the freezing points, the boiling points, and the KFs and KBs for those substances given on that table. And then we get to letter D, which we talked about in class. You need to take, there's 2 ways to do this. You can either, what is the effect of the ethylene glycol in the 160 grams of water? Calculate that, put it to the side. What is the effect of KBr in 160 grams of water? Calculate that, put it to the side. Then add the two effects for the freezing point, and then add the two effects for the boiling point change overall. And finally, the last one is, the last two are osmotic pressure calculations. And we won't bother to look at 12. It's pretty similar. Just notice the milligram unit right here. And otherwise, it's pretty similar to what we're going to do here for number 11, how we're going to look at this. So here for number 11, it says seawater contains 3.4 grams of salts for every liter of solution, assuming that the solute consists entirely of NaCl. Calculate the osmotic pressure. So here's the big deal. It says calculate the osmotic pressure. That's what we're solving for. And we have 3.4 grams of NaCl. Now they say salts here initially, but then they go on to say over here, assume that it's all sodium chloride. So we don't really need that information at this point. And we do. We need that to say that this is 3.4 grams of salt. It also says right here for every liter of solution, it's kind of hidden in the fact that it's in words, but it's not hidden, but sometimes we overlook things that aren't numerically represented. So we're going to consider that 1.00 liters of solution just to give it at least 3 sig figs right there. So the equation you'll recall from the first page for osmotic pressure right here is that pi equals I times capital M times R times T. So let's work with that. So pi is equal to I times capital M times R times T. This is the Van Hoff factor again, and for sodium chloride, that will be 2, because sodium chloride will break up into a sodium ion and a chloride ion. So the Van Hoff factor is 2. The molarity we have to calculate still. We'll come back to that in just a second. R is the constant. We used it in gases a lot. Technically, we're not in gases right here, but it still applies in other situations, not just for gases. In this case, 0.0821 liter atmosphere per mole Kelvin is our value. And notice I write all the units out because we want to look at those units and see if they're canceling out, if they're not canceling out, that kind of stuff. So, and then the temperature. It's at 25 degrees Celsius for my problem. So when we add 273 to that, we're at 298. So 298 Kelvin. Kelvin cancels out. And we want to find our molarity. So, because we have this piece right in here that we have to put in. So we've got 3.4 grams of sodium chloride. Let's take the 3.4 grams of NaCl and convert that to moles. When you look at the periodic table, 58 sodium at 22.99 and chlorine 35.45 adds up to 58.44. So that's our molar mass. And then we're going to divide that by the 1.00 liters of solution. So let's see what we got here. 3.4 divided by 58.44, and then divided by 1, of course, is going to be the same number. So it's 0.0582, 3.4, 0.058 with 2 sig figs. So 0.058 molar. And so let's drop that in right here now, 0.058. And I'm going to write the units as moles per liter for purposes of seeing how things cancel out here. And so let's zoom in a little bit more just on that calculation. And you can see that the mole cancels with the mole here. The liter cancels with the liter here. The Kelvin has already canceled. That leaves it with units of atmospheres, which are units of pressure, which is what we're trying to solve for. And so now it's just doing the work. So let's get the calculator over here, and 2 times 0.058 times 0.0821 times 298. There we go, 2.83 atmospheres. That's not a very high. I mean, that's a pretty significant pressure right there. I was thinking 2.8 millimeters of mercury, but 2.83 atmospheres. It's pretty significant osmotic pressure right there. So, all right, there you go. I think we'll call that for now because it's got pretty long here. All right, let's cut. Where's the stop button? There it is.